So in the first paragraph containing question number 7, 8 and 9, it is given that 1 mole of an ideal monatomic gas undergoes two quasi-static processes AB and BC in sequence. Process AB is isochoric heating, and in process BC, pressure is directly proportional to volume, and pressure at point C is equal to 2 times pressure at point B. Based on given information, answer the following questions. So in question number 7, the process ABC as shown in the process diagram will be like, so we have to find out the relation between P and V and T and V. So as I see, the process AB is isochoric heating, so volume is constant and the temperature is increased, then the pressure will increase. So AB is the right representation, and in the process BC, pressure is directly proportional to volume. So P is proportional to V. So if P is proportional to V, then it is a straight line equation passing through the origin. So option A is correct and B is wrong. As I know, P is proportional to T by V, so this can be written as T is proportional to V square. So if I draw the plot between T and V, then in the process AB is isochoric heating. So as the pressure is increased, so the temperature will increase. So this representation of AB is correct. And in the process BC, T is proportional to V square, which is a upward parabola. So option C is correct and D is wrong. So the correct answer for question number 7 are option A and C. Let's move to question number 8. In question number 8, if WBC is the work done in process BC, delta QBC is heat exchange in process BC, and TB is equal to 300 Kelvin, then we have to check the validity of given options. So we know that P is proportional to V. So if I find out the relation between pressure and temperature, then it can be written as V can be replaced by T by P. So T is proportional to P square. So we can say that Tc by Tb is equal to pressure at point C, that is 2 times Pb divided by Pb whole square. So from here, the temperature at point C is 4 times the temperature at point B, that is 300 Kelvin. So if I solve this, it comes out to be 1200 Kelvin. So in the process BC, temperature difference delta T is 1200 minus 300, so it comes out to be 900 Kelvin. So we can see that option A is the correct answer. In option B, delta QBC. So in order to calculate delta QBC, first of all I have to find out what is the heat capacity of this process BC. Since P is proportional to V, so we can write PV raised to the power minus 1 is equal to constant. So if I compare with the polytropic process equation, PV ki power x is equal to constant, then the value of x is minus 1, and the molar heat capacity can be written as CV. For monatomic gas, it is 3R by 2 plus R divided by 1 minus of minus 1, so that is 2. So it comes out to be 2R. So delta Q for the process BC can be written as N, that is 1, into CV, that is 2R, into dt, that is 900. So it comes out to be 1800 R. So option B is also correct. Now in order to calculate the value of WBC, we can find out what is change in internal energy in the process BC. So that is equal to N into CV, that is 3R by 2 for the monatomic, into dt, that is 900. So on solving, it comes out to be 1350 R. So from first law of thermodynamics, WBC can be written as 1800 R minus 1350 R. So it comes out to be 450 R. So option C is also correct. So the correct answer for question number 8 are option A, B and C. Let's move to question number 9. In question number 9, if delta is the thermal coefficient of volume expansion for the process BC, then we have to check the validity of given options. As I have already seen, T is proportional to V square. So if I differentiate this, 2 into dV by V is equal to dt by T. So if I write the delta, that is dB by V divided by dt. So this is equal to 1 by 2T. So delta is inversely proportional to T. So in the process BC, minimum temperature is at point B and the maximum temperature is at point C. So in the process BC, B is at lower temperature and C is at higher temperature. So we can see that B and C are the correct options. So the correct option for question number 9 are option B and C. Let's move to the second paragraph containing question number 10, 11 and 12. So in the second paragraph containing question number 10, 11 and 12, it is given that a heat conducting piston can freely move inside a closed thermally insulated cylinder filled with an ideal monatomic gas. At equilibrium, the piston divides the cylinder into two equal parts, the gas temperature being equal to T0 is equal to 300 Kelvin. The piston is slowly displaced towards right with the help of an external agent. So in question number 10, if delta U is the change in internal energy of the gaseous system, W1 is the work done by the gaseous system and W2 is the work done by the external agent, then we have to check the validity of given options. Since the cylinder is thermally insulated, so we can say that delta Q is equal to 0, and from first law of thermodynamics, if I write the equation for the gas, then work done by the gas, that is W1 plus change in internal energy of the gas delta U is equal to 0. Now the work done by the external agent is used in increasing the internal energy of the gas, so W2 is equal to delta U. So we can say that W1 plus W2 is equal to 0. Hence option A and C are correct and B and D are wrong. So the correct answer for question number 10 are option A and C. Let's move to question number 11. In question number 11, if T is the temperature of gas when displacement of piston is delta L, then we have to check the validity of given options. So let at any time T, the displacement is delta L. So corresponding to this volume is let V. So the work done by the external agent is Fdx or P1 minus P2 into dV. Let the pressure of this chamber is P1 and the pressure of this chamber is P2. Since the piston is displaced slowly, so the work done by external agent can be written as P1 minus P2 into dV, and this work done is used in increasing the internal energy of the gaseous system. So 2 times of internal energy of the gas in one part, that is NCV dt. So this can be further written as nRT into 1 divided by, let the initial volume of both the parts is V0, so V0 minus V minus of 1 divided by V0 plus V into dV, and this is equal to 2 into N into CV for the monatomic gases 3R by 2 into dt. So if I solve this equation, it comes out to be 2V dV divided by V0 square minus V square, that is equal to 3 times dt by t. So if I integrate, when delta L is 0 or V is 0, at that moment temperature of the gas is T0, and at the instant when delta L is delta L, V is V, at that moment the temperature is T. So if I integrate this equation, I will find T by T0 is equal to V0 divided by under root V0 square minus V square raised to the power 2 by 3. So if I substitute, the value of V is equal to V0 by 2 at delta L equal to L0 by 2, then at V equal to V0 by 2, the value of T comes out to be T0, that is 300 into 4 by 3 raised to the power 1 by 3. So option B is correct and A is wrong. And when the value of delta L is L0 by 3 or V is equal to V0 by 3, then the value of T comes out to be 300 into 9 by 8 raised to the power 1 by 3. So option B is correct and D is wrong. So the correct answer for question number 11 are option B and C. Let's move to question number 12. In question number 12, if F is force exerted by external agent on piston at displacement delta L, then, so we know that force is proportional to pressure difference, and the pressure difference increases because as the work done by external agent is positive, then the internal energy of the gas increases, so the temperature will increase, and as the temperature will increase, the pressure difference will also increase. So option D is correct, and if option D is correct, then option A is also correct. So the correct answer for question number 12 are option A and D. Let's move to the third paragraph containing question number 13, 14 and 15. In question number 13, variation of pressure P with time t at x equal to 0.05 meter is shown by. So if I write the equation of this straight line, then this can be written as P is equal to, slope is minus P0 by 0.05, as this separation is 0.05, into x plus the intercept on y-axis is p naught. So this is a px. So if I write this as p as a function of x comma t, then if the wave is traveling in the positive x direction, then x is replaced by x minus vt. So in that case, it can be written as minus p naught divided by 0.05 into x minus vt plus p naught. So if I substitute the value of x at x equal to 0.05, then if I substitute x equal to 0.05 here, then it comes out to be minus p naught plus p naught divided by 0.05 into v into t. So plus p naught. So this p naught get cancelled out. So if I take the slope of p versus t, then dp by dt is positive. So if I check, then option A is correct and C is wrong. Similarly, if the wave is traveling in the negative x direction, then x is replaced by x plus vt, and we will find that the slope will be negative. So option B is correct and D is wrong. So the correct answer for question number 13 are option A and B. Let's move to question number 14. Question number 14. If y is displacement of medium particles at x at t equal to 0, then variation of y with x may be. So if I check the options, then we know that the shape of y-x curve does not depend upon the direction of propagation of wave. So option B is correct and C is wrong. Now, as I see in option A and D, it is asked what is the variation of y with respect to x, which is the possible. So in option D, at this point, this function is non-differentiable. So D is wrong, and this is a differentiable function. So the variation of y with respect to x may take this shape. So option A is correct. So the correct answer for question number 14 are option A and B. Let's move to question number 15. In question number 15, if P naught is equal to 40 Pascal, rho and A be the density of medium and maximum acceleration of an element of air particle in the medium, then find out the value of rho and A. So we know that velocity of particle is equal to velocity of sound in medium into partial derivative of y with respect to x. And we know that P is equal to bulk modulus B into del y by del x. So if I substitute the value of del y by del x from here, then it comes out to be velocity of sound divided by bulk modulus into P. So the acceleration of particle can be written as derivative of the velocity of particle. So I can write in this way, Vs by B into partial derivative of P with respect to t. Now the partial derivative of P with respect to t can be written as partial derivative of P with respect to x into partial derivative of x with respect to t. Now this partial derivative of x with respect to t is the velocity of sound in medium, so that is Vs, and the partial derivative of P with respect to x, as I found from the figure given in the question, this is equal to slope, that is P naught, divided by 0.05 or x naught. So if I substitute this data here, so this is equal to Vs square into P naught divided by 0.05 into B. So if I substitute the value of all these variables, then I can find out the acceleration. So Vs is the velocity of sound in medium, that is 330 square, into P naught, the value of P naught is 40 Pascal, so 40 divided by 0.05 into bulk modulus. So bulk modulus value is 142 kilonewton per meter square, so into 10 raised to the power 3. So if I solve this, it comes out to be 614 meter per second square. So option B is correct and D is wrong. Now, in order to calculate the density, so rho can be written as B by V square. So this can be written as 142 into 10 to the power 3 divided by velocity of sound in medium, that is 330 square. So if I solve this, it comes out to be 1.3 kilogram per meter cube. So option C is correct and A is wrong. So the correct answer for question number 15 are option B and C. Let's move to question number 16.